Hello everyone. In this particular video, we're going to learn some oxidation reactions of alkenes. Okay, so that's going to be the theme of this video. So oxidation reactions of alkenes. So all the reactions that we're going to see in this video, we're going to be adding some oxygens to the alkenes, okay? And they're going to be added in various forms, but by the end of it, there will be an oxygen added to the molecule. So that's one way of looking at an oxidation reaction. Now, oxidation in general, I want you to realize that the basic definition of oxidation does not change. It is the loss of electrons. That is the fundamental definition of an oxidation process. But in organic chemistry, this addition of oxygen to a molecule can be viewed as an oxidation. You know, so it kind of makes it easy to identify an oxidation. If you have a molecule and if oxygens are added, then you can call it an oxidation reaction. Okay, so the first one that we're going to see here is an epoxidation reaction. Okay, this is an epoxidation reaction. And what this reaction does is it converts alkenes into epoxides. Epoxides are very important compounds. This is pretty much what's there in epoxy resins or the epoxy glues that you buy, that those contain epoxides, okay? That is what these epoxides are. So they are made from alkenes using this reaction, the epoxidation reaction. And for doing this reaction, what's important is you need a reagent, okay? You need a reagent for doing this reaction. And the reagent that we use for doing this reaction, in general, we can call that reagent a peroxy acid, okay? It's a peroxy acid. Now, I'll show you what this is, you know, chemically. A peroxy acid is represented as RCO3H. So 3 oxygens and H. Compare this, okay, so RCO3H, this is R C double bond O O O H. So that's a peroxy acid. So I think an easy way to actually be able to like visualize this and recognize this is to compare this to a carboxylic acid, which is RCO2H. So 2 oxygens, and we've already learned that as a functional group. So that's RC double bond O, OH. So a peroxy acid, this has an extra oxygen here, okay? That's how it's different from a carboxylic acid. So peroxy acids are going to be the reagents that we will be using for epoxidizing alkenes, okay? So let's look at the reaction. What is this reaction here? So essentially, if we have an alkene, okay, when we react this with a peroxy acid, RCO3H, this is an alkene, and when we do this, our product is an epoxide. An epoxide is a cyclic ether, okay? So this is an epoxide. It's a cyclic three-membered ring ether, okay? So not any cyclic ether is an epoxide, but when you have, and remember, ethers are when you have an oxygen between 2 carbon containing groups, and that's what we have here. We have an oxygen here, and there are 2 carbon containing groups. They're part of a 3-membered ring, okay? So that's what an epoxide is. Now, as you can notice here, I'm showing some stereochemistry here. I've put both of these bonds on a wedge, okay? Or I'm trying to say they're basically syn, okay? So the epoxide, this is formed with a syn stereochemistry, okay? So we cannot have one of these bonds on a wedge and the other one on a dash, okay? They're both wedges or they're both dashes, okay? Which again, in this particular case would give us a meso compound, okay? If we were to do it, because there will be symmetry in that molecule. Okay, now, so what is the mechanism of this reaction? This is another example of a mechanism of a concerted process. Okay, so the mechanism is a concerted process. That means everything happens in one step. All the bond forming and bond breaking events, they take place in one step simultaneously. Okay, so for this alkene, when we have this alkene, and we're going to write down this this peroxy acid, I'm going to write it in a certain way, to show this mechanism. Sorry. Like that. Okay, so this is RCO3H. That's a peroxy acid. And like all other reactions of alkenes, the alkene always acts as a nucleophile here, okay, because it has that pi bond. So because of that, it acts as a nucleophile. So what happens in this reaction here is the alkene goes and attacks this oxygen here. Okay, it attacks that oxygen, which is connected to that hydrogen there. Okay, the pi bond attacks that oxygen. As that happens, we break this bond here. It comes down. Okay, it tries to do sort of resonance here. It comes down here, and the other pi bond here opens up. It grabs that hydrogen. Okay, so several movements, electron movements happening here. So we've already done 1, 2, 3. So the pi bond attacks this oxygen, the terminal oxygen, sort of in the peroxy acid. The oxygen-oxygen bond breaks, and it goes and becomes a double bond between carbon and oxygen. The pi bond between carbon and oxygen opens up and grabs that proton, and at the same time, this sigma bond here, it comes and attacks this carbon back. Okay, so 4 electron pushes all happening at the same time, and because of that, what happens is this process is concerted. Everything happens at the same time, and what we get in the end is this oxygen. So we get the epoxide. So now this oxygen basically has been chopped off from the rest of the molecule. Okay, we're going to get that oxygen. Okay, so we get the epoxide here. We've got the epoxide, and along with that, if you look at everything else, we have R, and there is a double bond to this oxygen here. There is a single bond to the oxygen on the right. Okay, and this oxygen is now connected to the hydrogen, which basically is a carboxylic acid. So that's a carboxylic acid, RCO2H. So when we use the peroxy acid for oxidizing or epoxidizing this this olive or the alkene, what we get is an epoxide, and we get a carboxylic acid as our side product. Okay, so this is our side product. This is our side product. We are interested in the epoxide. Okay, that's the product that we are going to be focusing on. So that way we can basically oxidize an alkene. Okay, we can oxidize an alkene into an epoxide. So this is the first oxidation. Now epoxides are useful because we're going to see something here. Okay, epoxides are useful because epoxides ring open under acidic conditions to give anti-dihydroxylated products. Okay, they give us anti-dihydroxylated product. And what does that mean? So essentially what that means is if we start with this epoxide that we have, and I'll show you another example of this. Okay, if we start with this this epoxide that we have, if the conditions are acidic, so that means we have some acid around, the epoxide ring opens to give a diol. Okay, so we get a vicinal diol, so we can call it a vicinal diol. And as you can notice, the stereochemistry is anti, because they are anti to each other, the two hydroxyl groups. Okay, so it's an anti-stereochemistry here. Now, the mechanism of this reaction is very similar to like the ring opening of a bromonium ion. So I would encourage you to look at the textbook and maybe practice that mechanism, and you're going to see this again in 3150. Okay, for some part you're going to see this again in 3150. So basically the epoxide can be ring opened under acidic conditions to give us an anti-dihydroxylated product. Okay, so let's look at an example of this. So let's say if we have an alkene, and if we react it with a peroxy acid. Now, one of the most common peroxy acids that's used is MCPBA. Okay, MCPBA is metachloroperoxy benzoic acid. Okay, metachloroperoxy benzoic acid, and MCPBA, the structure of this molecule is like that. Now, I think again you should be able to recognize it. I don't want you to memorize this structure. You can use MCPBA, you know, when you're working through this. So be able to identify MCPBA. If someone's drawn that out, be able to recognize that. Okay, so MCPBA is, again, you're not familiar with this nomenclature yet, but this chlorine is meta on this aromatic ring. So it is a metachloroperoxy benzoic acid. That's what it is. Okay, so let's take that away. So if we epoxidize this alkene using MCPBA, which is basically a peroxy acid. Okay, this is a peroxy acid. So if we epoxidize this alkene, we will get an, if we do this reaction, we will get an epoxide. Wherever the double bond was, we get a 3-member ring over there. And now if we react this with acid, okay, so this is the epoxide, and now if we ring open it with acid, then we will get a diol. Now in this particular case, I've drawn it as Syn, but it is actually anti, when it's formed, it should be an anti-stereochemistry, but it doesn't matter here because there is only one chiral center here, so the Syn and the anti don't really matter here. Okay, there is one chiral center in the molecule. If there were 2 chiral centers, then it would be important. Okay, it would be important when there were like if there were 2 chiral centers in the molecule. But that would be our anti-dihydroxylated product. You will get 2 hydroxyl groups over here. Okay, there will be 2 hydroxyl groups on those carbon atoms. So that's the epoxidation of alkene. So one way of adding an oxygen to an alkene. And it can be used for making the anti-dihydroxylated product. Now, the second reaction that we're going to see is a Syn Dihydroxylation. Okay, how do you make, or how do you do a Syn Dihydroxylation on alkene? So what this does is it converts an alkene into a vicinal diol again, but in this particular case, it is going to be a syn diol. Now, the textbook has several examples of reagents that can be used. So, reagents that are used in this particular case, again, you identified them by maybe one of the reagents. So, osmium tetroxide is one of the reagents. This is usually used with some oxidant like NMO, or it could be a peroxide. And again, being able to identify, or maybe like putting down like one of these combinations. So this is one combination that can be used, or another easy combination, a reagent that you're already aware of, is potassium permanganate. You've learned this in Gen Chem. Potassium permanganate, as long as this is cold under basic conditions and there is base around, okay? So sodium hydroxide and water. If you have this, then it will also give you a Syn Dihydroxylation. So let's look at what a Syn Dihydroxylation is, okay? So essentially, again, I like these ring compounds to show the Syn Dihydroxylation because it's easy to see. So if I take this ring compound and let's say if I have permanganate, we have KMnO4, cold under basic conditions, then this would give me a diol which is syn. So you can notice that both hydroxyls are now on wedges. So this is a vicinal diol and it is syn stereochemistry. And this is a meso compound. Okay, this is a meso compound, so no point drawing the enantiomer. So that's the Syn Dihydroxylation. Now, the mechanism of this reaction, okay, this basically happens in 2 steps, but does have a concerted process there. So the mechanism of this reaction involves, again, there is a concerted process, but then there is a second step to it, okay? So the first step is sort of concerted, well, not the entire mechanism is concerted, okay? The entire mechanism is not concerted, okay? But the first step has several electron pushes that happen at the same time. So when we have permanganate, this is the permanganate ion, MnO4 minus, okay? The potassium is again just balancing the charge, so this is minus. So that's what we're looking at. So again, the alkene acts as a nucleophile. The pi bond goes and attacks that oxygen. The electrons from here go to the manganese, and then the pi bond here opens up and comes and attacks the alkene. Okay, so electrons from there go to the manganese, pi bond from there comes and attacks the alkene. And so what this gives us is an intermediate where the 2 oxygens now added from the same face. That's how we get the syn stereochemistry. So this is the concerted part of the mechanism. Okay, get manganese, O minus, double bond, got oxygen over there, and there are 2 electrons on that manganese. Okay, these oxygens, they have their lone pairs, all of them. They have all their electrons. Okay, so we get an intermediate like this. This intermediate is called a manganate ester. Again, you don't have to like memorize these names, but I'm just showing you what the mechanism looks like. Okay, so that's called a manganate ester, and this manganate ester under basic conditions, that's why we need the base. Under basic conditions, this manganate ester gives us the syndiol, and the manganese part of it actually becomes manganese dioxide. Okay, it becomes manganese dioxide, MnO2. And so for that reason, this reaction is like stoichiometric, because your permanganate becomes manganese dioxide. So you cannot really use it over and over again. With the other reagent that I had written, the osmium reagent, you could do it catalytically in presence of an oxidant. You could recycle it, okay? And that works well because osmium is a very expensive, like it's a pretty expensive metal compared to manganese. And so something cheaper, you can use it as a reagent stoichiometrically, but the osmium, you want to recycle it as much as you can. Okay, so this is another reaction that basically adds oxygens to alkenes. Compare it to the epoxidation. The epoxidation makes an epoxide, and then you can ring open it to give the anti-diol, dihydroxylated product. Syn dihydroxylation using permanganate or osmium tetroxide gives you a syn diol. Okay, vicinal diol in both cases, but in this cases it is a syn diol. So that's an oxidation reaction. One last reaction, oxidation reaction, that we will not go into too much details. Okay, we will not go into too many details of this reaction. This is an ozonolysis. Okay. What ozonolysis does is it converts alkenes into carbonyl compounds. Okay, it converts alkenes into carbonyl compounds. And just to give you an overview of what happens in this reaction, you react an alkene. Okay. You react an alkene, let's say we have R and R prime. In this process, which is done stepwise, you react the alkene with ozone. Okay, this is the ozone that's in the atmosphere, okay, the ozone layer that we talk about. Okay, ozone can be used as a reagent. You react with ozone, and this is usually done at low temperatures, so very low temperatures. And then secondly, you use a reducing agent. You could use zinc, or you could use like dimethyl sulfide, one of those two. They're both reducing agents. And essentially what you get at the end of this is two aldehydes. Okay, we get that. So now if you look at it, if you compare your products to your reactants, what we've done is we've essentially cleaved this double bond here, and we've added oxygens to both of those carbons. Okay, we had the carbons that were part of the pi bond. We added double bonds to both carbon atoms. So we got two aldehydes from there. Now, if we start with a different alkene, let's say if our alkene is tri-substituted, let's say that's the alkene. And if we do an ozonolysis on this, so ozone, second step, and let me just use one of the reductants. So let's say we use zinc as the second step. You can use any one of those two. Okay, let's say if I do zinc, again, it's going to cleave here, and it's going to add an oxygen on both ends. So the product that we will get is going to be a ketone on the left-hand side plus an aldehyde from the right-hand side, because there is a hydrogen here, okay? There was a hydrogen here, there is a hydrogen here. That's why we're getting aldehydes. We got two aldehydes there. From a di-substituted alkene, we got two aldehydes. From a tri-substituted alkene, we get one ketone, one aldehyde. If it were a tetra-substituted alkene, we're going to get two ketone products, okay? That's how this reaction works. We will not go into the mechanism of the reaction itself, but now let's look at like maybe two examples quickly, okay? So let's look at two examples. So if we have an alkene, and if we do ozonolysis on this, it's going to break in between, and our products are going to be a ketone. I added an oxygen in this side. I'm going to add an oxygen on the other side. So I should get that aldehyde. There are two hydrogens here. That's the simplest aldehyde that's possible. This is formaldehyde. Formaldehyde, okay? But we get a ketone and an aldehyde. If it were something like a straight chain like this, and we do this reaction, ozone and two, let's say we do zinc, we break it here, there is a hydrogen here, hydrogen there. Since it is a di-substituted alkene, I should get two aldehydes. And in this particular case, if you look, I have 1, 2, 3 carbons to that double bond, 1, 2, 3 carbons to that double bond. So that means from this reaction, I should get two molecules of this aldehyde. That will be my product. Now, that's because the molecule was symmetrical, okay? That's why I got two molecules of the same aldehyde. If it were not, then I would get different aldehydes, okay? So that's the ozonolysis reaction. Again, we're not going into the mechanism of that reaction. It's a little complicated. And for us, I think being able to like identify these products, that should be more than enough, okay? And it is a very useful reaction, because like in a few decades ago, I would say, like, you know, like in the early years, what people would do is, if you had a molecule and if you somehow knew that it was an alkene, but if it's a really big molecule and you couldn't predict what that big molecule was, you would do an ozonolysis on it to break it down into smaller chunks. And then you analyze the smaller chunks, and once you know what the smaller chunks are, then you can basically put those together to predict what your starting material was. Because if you look at it, if these are two products that I get, then when I chop off these two or when I remove these two oxygens and connect the two fragments together, I can identify what the starting alkene was. Or if I get two of these aldehydes, take two of those, remove the oxygen, connect the two halves together, I know what the starting material was, okay? So this was very good in that way, in terms of like analysis and figuring out what a big molecule might have been. So that's the third of the oxidation reactions, okay? So we learned epoxidation, which can give us the anti-dihydroxylation product. We learned Syn Dihydroxylation, and then finally ozonolysis. We didn't go into a lot of detail for the ozonolysis, but just very, you know, brief overview of what ozonolysis does.